Hello everyone, welcome to this recording sessions on deep learning topic. So this is Akhil from VNR VJET from the Department of CSE Data Science. So we are going to see in this lecture recording session some deep learning terminologies and their concepts elaboration. So most of them asked me what is the difference between what is neural network, what is deep learning, so what is the difference between them, why do people often call sometimes neural network, why do some people often call deep learning as in sometimes. Okay, so I can clear this doubt in this session. So neural network, so neural network is nothing but when we have less number of neurons we can call it as neural network, and if we have more number of neurons then we can call it as a deep learning, right? So that is the difference between neural network and deep learning. There's nothing much difference between them. It depends upon the how many number of neurons. Yeah, in these sessions we'll be covering these terminologies: what is neuron or perceptron, then what is activation function, what is cost function, what is back propagation, and what is gradient descent function. So these terminologies we'll be covering in this lecture recording. Okay, so let me talk about the first terminology, neuron or perceptron, right? So let us understand this diagram picture representation. What is this? This is a human neuron, how it looks like. So it has dendrites, nucleus, cell body, axon terminals, right? So all the inputs that the user has receiving, say suppose if I'm receiving some information or instructions from the outside, so how it will goes, it will goes through the dendrites part. So output information is captured through the dendrites. Okay, from these dendrites and with the help of nucleus it process through this cell body, and it goes on with the axon, and it goes on to the axon terminals. Okay, axon terminals. So in this axon terminals we have another neuron attached to it, similar to this. Okay, similar to this we have another neuron attached to it. So again the dendrites, another dendrite from another neuron will capture this information from these axon terminals, and with the help of nucleus and with the help of cell body and with the help of axon, it will again propagate the information and pass the information to the another cell. So this process will occur throughout the entire information process in the human brain. Okay, so now why can't we create this, right? Humans are humans are able to receive the information from outside, replicate it, uh, process the information and react how they want to react in the terms of output, right? So why can't we uh, create a software based approach, thinking like a human and acting like a human, right? There comes the picture, neuron. Okay, so mimicking the human brain is called as neuron. Okay, you can see the definition here. Artificial neural network, ANN, is a software based approach to replicate the biological neuron. Okay, it is a software based approach that mimicking the biological neuron. So this is the diagrammatic representation of the software based approach neuron. Okay, so here you can see the inputs x1, x2, x3, x4, x5 and so on up to xn, and weights w1, w2, w3, w4 and so on wn, all together are getting processed here. Okay, all are getting processed here. So in this process there is a bias is also getting added here, and there is also transfer function or activation function coming into this picture. So and then we are getting the outputs here. Okay, we are getting the outputs here. Okay, so this is the diagrammatic representation or pictorial representation. You can also represent this in the form of mathematical representation like this. So b naught is the bias, and we can add summation symbol here. So from 0 to n we have weights. We have seen x1, x2, x3, and so on xn, right? And w1, w2, w3 and so on wn, right? So all this gets summed up here. So all this gets multiplied here and summed up. So b1 into w1 plus b2 into w2 plus b3 into w3 plus and so on. Okay, and so on. We'll be adding till n. So to all the summation, we'll be adding the bias. Okay, v0 is the bias. So this entire equation is called as mathematical representation of a perceptron. Okay, this entire equation is called as mathematical representation of a perceptron. Okay, and we can also represent the neuron concepts in the pictorial form in this way also. We have inputs, we have hidden layers. So each input is connected to the hidden layer like this. So this is my x1, x2, x3, x4 and so on it will be. So x2 will be given to hidden layer, next hidden layer. So again this will be given here, this will be given here. All together will be capturing here the output. So this is hidden layer. So what is hidden layer? What is hidden layer? Why we need hidden layers? Hidden layers are nothing but they are the covers. They are the covers just acting like a protection layer to the input neurons. Okay, so that's why we need hidden layers and to protect the neurons. Okay, so and this slide shows the activation functions. What are activation functions and why we need them? So which activation functions to use when? So there are many activation functions like step function, sigmoid function, hyperbolic tangent function, Rayleigh activation function and softmax function. Okay, so there are many, right? So when to use activation function, this is also one of the most important concepts in the deep learning concepts. So many people don't know when to use activation function, which activation functions better, in what scenario, which activation function maybe I need to select. There may be a discussion or a debate in most of them. So I can suggest softmax functions, activation functions can be used for the multi-classification problem, and sigmoid activation functions can be used for the binary classification problem. Remaining all, depending upon the problem, depending upon the regression problem and all, you can go with the remaining activation functions. But for in case of classification, binary and multi-classification, we can use these two. Okay, and then next comes the one of the most important activation function is Rayleigh activation function. Rayleigh activation function is one of the most important function that is used to train hidden layers. Okay, it is mostly used to the hidden layers rather than the input neurons. Okay, and I would also like to add and bring to the notice that why Rayleigh is important, that much important when compared to remaining all activation functions. When there are many activation functions means Rayleigh activation functions will avoid gradient descent problem. Gradient descent problem. So when we are using sigmoid function and softmax function, we mostly face gradient descent problem. So in order to avoid that, we go with the Rayleigh activation function. So understood, right? So mostly we can go with the Rayleigh activation function, or else second priority can be given to the sigmoid activation function or softmax activation function. Okay, then comes the remaining all activation functions depending upon the problem statement. Okay, yeah, this is the pictorial representation of the activation functions. So this is a step function. You can see for 0, you can see for less than 0 we have negative values, for greater than 0 we have the value as 1. Okay, so this is the step function or unit function. Next, this is the sigmoid function. Okay, this is a sigmoid function and the equation is 1 by 1 plus e power minus x. Then hyperbolic tangent functions. We can see cos h, sin hx, tan hx, and their equations here. Okay, and the graphical representations also here. And this is how the Rayleigh activation functions looks. So it is like for except for the values for greater than 0, it is like this. For 1, it is 1. For 2, it is 2. For 3, it is 3. Okay, for it. Okay, so this is how the Rayleigh activation function graph looks like. Yeah. So before going into the cost function, loss function, or error function, let me talk about this pictorial representation. This pictorial representation of the entire process of the deep learning. Yeah. So once again, we can recall that x1, x2, x3 are the x1, x2, x3 are the inputs that will be giving. W1, W2, W3, W4, and so on, Wn are the weights that will be giving. So inputs and weights all together get summed up here. Okay. So during this summed up, we'll add bias. There are different biases like Adam. Adam is the one of the most bias that been used by many of the people. So, and there are many other bias also that we can consider. Okay, so we'll be adding bias. So why we need bias, right? Why we need bias? We need bias for the propagating the neuron. Say suppose why I need bias? To be proactive or to be well functioning to give output, right? In the similar way, neuron also need bias. Neuron needs bias to give a proper output. Okay, without any disturbance. Okay, then comes the, after all this summation and bias, we'll be adding the transfer function or activation function. So here what happens, why we need activation functions means in order to avoid the loss of information, and to make the neurons active. We can say with the help of bias also the neurons will be active, and with the help of activation functions also the neurons will be active, and they are able to give the proper output and a good output. We can expect the good output with the help of activation functions. So that is the role of the activation function. So we will be getting y1, y2, y3, and so on, yn for the values x1, x2, x3, x4, and so on, xn values. We are getting the values. Yes, we got. So these are predicted ones, predicted values. Okay. So whatever the values that have been predicted, are they correct? Are they good? We don't know, right? So in order to know that, we need to calculate using the one mathematical function. We need to calculate how good the prediction is. So that is nothing but a cost function, loss function, or error function. We can call it as cost function, we can call it as loss function, we can call it as error functions. So these three names are for the same. So here what we'll do, we will predict. We got output y is, right? So we are here, y can be considered as a, because I'm considering y as the actual output. In the diagram it is y as the predicted output, but here I am considering in the mathematical equation, I am considering y as the actual output and a as the predicted output. So we will be seeing here, so actual values minus predicted values by n. So n is the number of neurons, so we'll be calculating it. So if we have 0.5 and as the 0.5 as the actual value and 0.2 as the a value, then we can subtract 0.5 minus 0.2, 0.3 whole square by n value. So that will be the c value, nothing but a cost function. So this cost function we can use it to plot it here. Say suppose for the cost function 1, I got a graph representation like this. So this is for the first prediction of y values, first prediction of y values. Okay, so I got here. Okay, so what is the difference between the actual and predicted values? If you see the gap, see how much it is we are getting, right? This much gap. So there is more gap between the actual value and the predicted value. So what we need to do? What we need to do? We need to come here again, and we need to send all these outputs as the inputs. Okay, for the second time. First time we got. For the second time, we'll give all these predicted values y1, y2, y3, y4, and yn, all this as inputs. So this all y1, y2, y2, and yn, so on yn will be considered as x1, x2, x3, x4, x5, x6, xn. Okay. So again, the same process will happen. So again, x1, x2 will be summed up with w1, w2, and bias will be getting added, and again it will be passed to transfer function, and from the, after transfer function we'll get the outputs y1, y2, y3, y4 for a second time. Okay, second time. And for the second time also, if you calculate the cost function or loss function or error function, how much we are getting, if you plot it, we are getting it here. Okay, still the error, if you could see the difference between graphically, you could see for the second time, okay, my model could match the actual value and the predicted values are somewhat closer to each other when compared to the first time. This is second time. Okay, so what we need to do, again we need to repeat this process, entire process again for the third time. Third time also we'll repeat this process, and this entire process will happen again, and we'll get the y1, y2, y3, y4, yn, and up to yn for the third time also. Again for the third time also we need to calculate cost function or loss function or error function for the third time and plot it third time. See, and again for the fourth time. See, if we go on back propagating, so this is nothing but a back propagation, giving all the outputs as a inputs again, right? We are giving all the inputs as a, all the outputs as a inputs. We are back propagating it. So this entire process is called back propagation. That means we are sending all the output values to be considered as input. So this is called back propagation. Okay. So now we have seen what is back propagation also. So if I apply back propagation for the fourth time, I'm getting like this. If I apply back propagation for the fifth time, I'm getting like this. If I am applying back propagation for the sixth time, I'm getting like this, and so on for the seventh time, 8th, 9th, 10th, and 11th, I may get here 12th, 13th, 14th, right? So how long we'll apply this back propagation techniques? Right? We don't know when to stop the back propagation, right? So we need to stop. We need to stop back propagating where we'll get the minimum value, or we can call it as global minima. So the point where we get a minima, global minima, or minimum value or local minima, so here we need to stop it, because the difference between the actual value and the predicted value is very, very less. So if we keep on repeating back propagation, the output may be increasing. Okay, then the variations will be also between the actual value and the predicted value is also increasing. Okay, it will be increasing. Okay, we need to stop here. Okay, so this entire process of finding a point in a back propagation is called as gradient descent. Okay, this entire technique is called gradient descent. So gradient descent is a technique to find local minima or global minima in the back propagation, so that we can stop the back propagation technique at one particular point of time. Okay, yeah, this is the cost function or loss function or error function for the binary classification. Okay, this is for multi classification. So we have activation functions, different activation functions. We have loss functions, we have different loss functions or error functions, right? So error functions, right? So for binary here also, for binary classification problem, we can use mean square error. So mean square error technique is we have mean square error, loss functions, mean square error, binary cross entropy, sparse categorical entropy. And there are few more techniques also that are available in the calculation of loss functions. So we will use mean square error for the binary classification problem and binary cross entropy also for binary classification problem. And we use sparse categorical cross entropy for multi-classification problem. And this is the mathematical equation to calculate the loss function for multi-classification problem. Okay. So this is how the cost function is calculated for the binary classification as well as a multi-classification. So on together we can say depending upon the problem or depending upon the problem statement or case study or whatever we can say, we need to select the right activation function, right loss function, and right parameters, right optimization technique also depending upon the problem statement. So I think I have covered all the terminologies that are required for the deep learning, main terminologies. I have covered what is neuron or perceptron. It's nothing but a software based approach of a biological neuron representation, and activation function, cost function, gradient descent, and back propagation. Okay, thank you all. Thank you for this opportunity. I thank one and all. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.